Today we're going to talk about electric fields, and I want to start by reviewing gravitational fields because we've already talked about gravitational fields, and then based on that we're going to define what an electric field is. And these are both force fields, and you've probably heard of force fields in science fiction and so on, but here we're going to get to the real thing, what force fields really are. Then we're going to calculate the electric field, and that's the symbol for electric field, a capital E with a vector hat on it, for a point charge or a spherical charge. We're going to use Coulomb's law to do that. And then finally I'm going to show you how to draw electric field lines, and there's some rules for drawing electric field lines, and then I'll give you some little exercises to do, and then we'll see how well you do on those. So let's begin with gravitational fields. So let's review gravity for just a second. This is the ground, and I hold a rock or something above the ground. We know that there is a force on the rock. This is the force of gravity, the weight of the rock. Now, why does gravity happen? It's because objects that have mass distort the space-time continuum around them in such a way that they attract each other. All massive objects attract each other. And so the ground pulls the rock down, the rock's trying to pull the ground up, because of course the Earth is so massive that you don't see any change in the Earth's motion, but you do see the rock fall down. And we have a way of describing how strong the gravitational field is. We say that we take the force of gravity and we divide it by the mass of the object that's in the gravity field. See, gravity is caused by mass, and so if something has mass and it's in a gravity field, it will feel a force. If you take that force that it feels because it's in a gravity field and divide it by the mass, you've got the gravitational field. Now we call it G, and we know that if we release the rock, what is the rate of its fall? What is the rate of acceleration of its fall? It's 9.8, right, meters per second squared. But when we're talking about gravity fields, we would express it like this: 9.8 newtons of force per kilogram of mass. And this is a gravitational field. That is, you get a force field. You get a force depending on how much mass you have. Okay. Now, obviously, we had Newton's law of gravity that told us that the gravitational field gets weaker as the masses get further and further apart. I'm not going to review all of that, but we can just, this is what we did. We did this like back in October. We talked about the gravitational field strength near the Earth's surface, the strength of gravity per unit mass, force per unit mass. Okay, well, let's say that, let's define the electric field. So this is, let me relabel this. This is the gravity field. So now we're going to have the electric field. Well, if I have an electric field, here's what I've done. In order to get an electric field, I have to separate some charge somewhere. So let's say, way over here, I've got some positive charge that I separated from negative. Maybe I put the negative charge way over here, but I don't even really care about them except for this. If I put a little charge right here, and I'm going to call this Q naught. Well, this little charge is going to feel a force, isn't it? This was on the quiz today. It's going to feel like this little charge is going to be attracted to the negative and repelled by the positive, both of them are going to try to push them to the right with a certain force. Now, this force exists because this object right here has charge. So if you feel a force acting on you because you have a net charge, either positive or negative, then you are in an electric field. See, these guys right here, this positive charge and this negative, they distort the space around them in such a way that if you place an object that has charge in that space, it will feel a force. Now that's exactly what's happening with gravity, right? Where it's like I have the planet Earth below my feet, and I put an object that has mass. Well, it feels a force because it has mass. So this guy feels a force because it has mass. This guy feels a force because it has a charge on it. Well, we're now going to define the electric field. The electric field, we call it E for electric field, with a vector hat on it because it's a vector, is equal to the force that this charged object feels because it's in space. And I'm going to call that F sub E for electric force, divided by the charge that it has. And I'm going to call that Q naught. It's traditional to call the charge that you're putting in space to measure the electric field with our test charge. This is our test charge. We're using it to test the electric field, and we call it Q naught. Now, notice something here. This guy right here has a certain amount of charge on it. Our test charge has a certain charge on it. And if I place it in space right here, it feels this force because it has this charge. It has no idea why. It has no idea that there are positive charge and negative. It just says, hey, I'm putting it in space. I feel an electric force. So if I take that electric force, magnitude and direction, right? This is the electric force to the right, divided by the charge, and charge is a scalar, it doesn't have a direction. So the electric field has the same direction as the electric force that's on our test charge. So this is how we define electric field, and it's just like the way we define a gravity field. And later on we're going to talk about magnetic fields. They're a little more complicated, but it's the same basic idea. You're in space with a certain characteristic, and because of that characteristic, you feel a force on you. In this case, it's mass. In this case, it's charge. Mass, gravity field. Charge, electric field. Okay? And this is a very simple equation, isn't it? What units does electric field have? Well, if I look at this, this is measured in newtons, and this is measured in coulombs. So the electric field, the units for electric field are newtons per coulomb. Simple. So if somebody gives you an electric field and they give you a charge, you can figure out the force. Right? Because the force is just the charge on my object times the strength of the electric field. That'll give me the force. Or if I give you the strength of the electric field and how much force is on the object, you can calculate the charge. So I mean, you just use this as an equation like we have all here. Yes? Okay. Now let's calculate the electric field around a point charge. So E for a point charge, or a sometimes they call it a spherical charge, a charge with a spherical symmetry. So let's put some positive charge here, and let's say it's on a sphere, so I'll make it nice and round here. And then I put my test charge over here. Now I'm going to call this Q. And of course, what do I call my test charge? Q naught. Well, let me ask you this. What is the force between these two objects? Can we calculate it? Let's say the distance between them is r. Sure, I can calculate the force between these two charges. What do I use to calculate the force between 2 point charges? I use Coulomb's law. So the force between these charges is equal to K times Q, this one, times Q naught over the distance between them squared. Yes? That's Coulomb's law. And in what direction is the force? Well, it's in the r hat direction. That means away from. Now, it's traditional to always make your test charge, when you're trying to define what the electric field is, the direction of the electric field, you always define it by what would happen to a positive test charge. So the Q naught, and for the purposes of calculating the electric field, Q naught, our test charge, will always be a positive charge. So you'll always be able to tell what direction the electric field is in. Right? You got it? Staying with me? Focus. All right, so now let's figure out what the electric field is. Well, we said the electric field, by definition, is the electric force divided by my test charge. So here, I'm going to figure out what is the electric field at this point right here, r away from my from this point charge. So here's my point, or my spherical charge. I'm a distance r away from it. I'm going to use Q naught to figure out what is the strength of the electric field at this point. Okay? Now, one thing I forgot to mention earlier. Isn't this annoying that we're using the capital letter E? Because what did we use capital letter E for before? Yeah, mechanical energy. Well, folks, we've got more quantities to deal with in physics than we have letters. But there is a difference here. What does this E have associated with it? The specter symbol. Energy is a scalar. It doesn't have any direction associated with it. So you have to look at the context of the problem. Does E represent electric field or mechanical energy? And if you ever see it with a vector hat on it like that, that means it's electric field. Well, we have an equation now for the electric force. That's Coulomb's law. So this is going to be K, Q naught over R squared divided by Q naught in the R hat direction. Anything cancel out? What cancels out? Q naught. So I can make Q naught anything. It divides out. I mean, it cancels out of the equation. So the electric field for a point charge is equal to K times Q. That is the charge on my object that's creating the field around it, divided by R squared, where R is the distance from the center of that spherical charge. And what direction is that electric field going to be in? The R hat direction. Now what does R hat mean again? It means away from. So the electric field, and this makes sense, doesn't it? If I put a positive test charge right here, it's going to be pushed away from Q. So here's the electric field right there. And it is away from R. What if this was a negative charge? What if Q was negative? So let's put a negative spherical charge here. Okay, and here's my little positive test charge. Well, my positive test charge is going to be drawn to it. It's going to be pulled that way towards it. And you would see that because, look, this is a negative charge, isn't it? Q here is negative Q, and then you would just transfer that negative to the R hat, and negative r hat means towards. So this would give you the magnitude, kq over r squared, would give you the magnitude of the force, and you've transferred the negative over here, which means it's attracting that positive test charge. Yes? Okay. So E for a point charge or a spherical charge. When I say point charge, that means like the charge is all concentrated at a single point in space, is equal to kq over r squared in the r hat direction. So this is a basic equation. But you have to know that this is a definition of the electric field, or this is what you get for the electric field for a point charge. It doesn't work for all charge distributions. Okay. Now, finally, let's talk about how to draw the electric field. We're going to draw electric field lines. Now, let me tell you what electric field lines are for. Electric field lines is a way for us, drawing electric field lines is a way for us to visualize the space around a certain charge or a certain distribution of charge in space. It's a way of thinking about it. These lines don't actually exist. You can't get a microscope and see electric field lines, but you can imagine them there. Like if you're hiking and you look at a map and you've got topographical lines, a topo map, you got topographical. Well, there aren't really lines on the ground, but we use them to imagine how steep or how steep the mountains are. Same thing is true with electric field lines. It's just a way for us to imagine the space around a charge. So let's start off with a simple charge. Again, a spherical charge distribution, something like this. Let's put Q right here, like this. And then what I'm going to do is I'm going to put my little test charge right here, right next to it. Now, what is that positive test charge going to feel? It's going to feel a force, and it's going to be away from, isn't it? It's going to be away from this charge, because they're both positive charges. So I'm going to draw the force away from. Well, now I'm going to put my positive test charge right here. Now, what's it going to feel? It's going to feel a force away from this, a little bit weaker because I'm farther away. But then I can put it right here. And no matter how many times I have to do this, I can keep doing this forever. And so what I can do is I can hook up all these force lines together and make what's called an electric field line. Now, what if I started right here, put my positive test charge right there? Well, it would get pushed away from, and it would just go out like that. Like that. Like that. Like that. Okay? So, these are electric field lines, and they kind of tell you this. For this very simple point charge or spherical charge, no matter where I am, I'm going to get pushed away from that charge if I'm a positive test charge. Makes sense. But also, the field lines give you more information than that. Notice that the farther away I am, the farther apart the field lines are from each other. The farther apart the field lines are from each other, the weaker the electric field is. Okay, now, what if I were, this is going to be a completely separate problem. What if my spherical charge is negative instead? What's that going to look like? Well, let's start with our positive test charge right here. What would you draw? What direction is the force? Yeah, it's to the left. It's towards negative r hat. And then I put my positive test charge here. It's a little bit stronger because I'm closer. In fact, I could connect all these force vectors together until they go like this. If I started out here, it would point like this. Like this. Something like that. This would be a pretty good. Now, by the way, again, these are completely separate drawings, so we want to think of these as independent of each other. Think about this. If you've got a positive point charge right here, I had to, remember, the universe is electrically neutral. We've got just as much positive as negative charge in the universe, and most matter is in a state of being electrically neutral. But some object right here, I put a whole bunch of positive charge on it. At the expense of what? The rest of the universe. I had to take away electrons from this object, and I pretend that I've evenly distributed those electrons throughout the rest of the universe. So what I'm going to do is I'm going to pretend like way out here there's an electron, electron, negative charge. So all these the positive charge here, there's an equal amount of negative charge somewhere out there in the universe. And I pretend like these field lines go all the way here. Same thing is true with this. Here I've got negative charge. Well, that means somewhere out in the universe I've got positive charge. So let's say infinitely far away, I put positive charge, and then this field line comes in from infinity, where that positive charge started, and goes there. Now, one thing that we can see about field lines is that they start at positive charge and they end at negative charge. Those are two of the rules for drawing electric field lines. Now, let's combine these into the same diagram. What if I put some positive charge here, some negative charge over here? Well, ask yourself, what would a little test charge do? I'm going to get a little bracelet. What would a positive test charge do? Okay, sorry. Or, it says, I'm a little test charge, short and stout. Okay, and I'm going to go right here, and I'm going to get pushed away from the positive charge, but I'm also going to be attracted to the negative charge, and they're both pulling me in the same direction, which means I've got a field line that looks like this. That makes sense. That's pretty easy. There's my electric field line. Starts at positive, ends at negative. Now, what if I put my positive test charge right here? Well, now it gets pushed away. Look, it's so much closer to the positive than the negative that the positive force, the electric force from the positive charge totally overwhelms this, and so it's mostly pushed away. But then it's further away, and this one starts pulling it. So it says a little bit of influence. Then when it's right in between, they're equal. The force is to the right. And then it comes down like this. I didn't draw that very well, but here it goes like that. So it's curved. Now the field line is curving in space. And it's symmetric. Now, if I start it right here, I'm going to go way out here, and by the time this guy starts bending, I'm pretty far away. So I get a field line that looks something like this. And then symmetrically on this side, like that. Way out here, and then comes back in. Way out here and comes back in. Okay, and then finally Comes out like this and then comes in like this. Now there is an assumption here I didn't say. If this is positive Q and this is negative Q. That is, the charges are the same. So let's write the rules here. Field line rules for E fields. E field lines. They start at positive. They end at negative. Also, there's one thing. How many of you have seen the movie Ghostbusters? Yeah. Okay, what's the number one rule if you're a Ghostbuster? Never do what? Never cross the streams. What happens if you cross the streams in Ghostbusters? Okay, every atom in your body will explode at the speed of light, which means absolutely nothing, but it sounds good and it's funny. Here's something that will never happen. Field lines, you will never get a field line that does this, like boom. I just committed a great foul. No! Field lines never cross. And here's why. It makes total sense why you never cross electric field lines when you draw them. Put my little test charge right here. If you cross a field line, you're saying that when I add up the electric forces, they're going to push me in this direction and they're going to push me in this direction at the same time. Which makes no sense. They're going to push you in, when you add them together, they're going to push you in one and only one direction. This makes no sense. So, never cross field lines. If you do, 2 points will explode at the speed of light from your test. Yeah? See what I did? All right. Last thing. Let's take a look at something like this. If I have two charges and they're separated like this, and let's say one's negative, one's positive, and I'll get some field lines like this. I'm not drawing this very well, but I'm trying to go fast. Now, here's what's going to happen. Look, let's say there's 4 microcoulombs here and negative 4 microcoulombs over here. So I've got positive 4 and negative 4. What would happen if I added positive charge over here but didn't add negative charge over here? Everybody pay attention. I'm almost done. Bad students. Don't point at him. If I add, let's say I add 2 more microcoulombs of positive charge to this. So now I've got 6, but I left this negative 4. Well, that means that somewhere out here in the universe, there's negative 2 microcoulombs dispersed out there in the universe, right? Because the universe is electrically neutral. If I add positive charge here, that positive charge had to come because I put negative charge somewhere else. Well, where is it? Well, I'm going to pretend like it's evenly distributed through the universe. And so what I have to do is I have to show that by drawing more field lines. But these extra field lines don't terminate over here. They terminate somewhere out there in the universe, wherever I deposited that negative 2 microcoulombs of charge. Now what this means is the number of field lines I draw is proportional to the amount of charge. So that's my other rule I'm going to add here. The number of field lines is proportional to the charge.
Attention staff, please release all PASA members to the PASA.
Okay, now PASA members, away with you. Que pasa? I don't know. All right, now. Okay. And finally, by the way, the last rule is that field lines should represent the space around them. The space around the charges. Now, let me show you an example of when students violate that rule. And it's, by the way, this is the rule that I am the most lenient on. If you have like 1, 2, 3, 4 charges here and 1, 2, 3, 4 negative charges here, people will do this. They'll go, okay, 1, 2, 3, 4. Now, they haven't crossed any field lines. They've started at positive and they've ended at negative. The number of field lines is proportional to the amount of charge. But look, come on, what about all this empty space around it? You know, show some, have some finesse. Kind of show the space around the charge as much as you can. That is all. Perfect timing.